Hi students, welcome to this quick online video summary on the chapter of hydrocarbons. Right, so this is actually one of the first chapter on the concept of organic chemistry. Right, so before I get started, let me just quickly recap about what the term hydrocarbons mean. Right, so look at this page. I total only have 3 pages over here. Hydrocarbons, as the name suggests, refers to any compounds that only contain hydrogen, so the hydro, and carbon, right? So the compound entirely can only have carbon and hydrogen in its formula, right? So in our syllabus, there's only 2 of such types of organic compounds. One is known as alkane and one is known as alkene, right? Before we go on further to talk about the reactions, etc., let's get familiar with how to determine whether something is an alkane or whether something is an alkene, right? Because if you can't even see whether it's an alkane or alkene, there's really no point talking about finding out what's the reaction. So let's start with this first. Number 1, you can look at the name if the name is given to you, right? So if you look at this closely, you'll notice that all alkanes, the name actually ends with A and E. All alkenes ends with E and E. So that's the first way to tell whether you're looking at an alkane or are you looking at an alkene. The second way is look at the chemical formula if it's given to you, right? So when you look at the 2 chemical formula, you should recall that for alkanes, there's this thing called a general formula, CnH2n plus 2, whereby N refers to the number of carbon. And for alkene, the general formula is CnH2n. Similarly, N refers to the number of carbon. So let's try to apply this to some of the examples over here. If you look at this alkene, for instance, propane, given that there's 3 carbon here, if we apply the formula of CnH2n plus 2, it will mean that it will be C3, H2n will now be 2 times 3, which is 6, plus a 2, and therefore is C3H8. So when you look at the alkane formula, actually you can derive whether something is an alkane or not by looking at this CnH2n plus 2. On the right hand side, the alkenes. Let's take this for instance, propene. C3, that means the N is 3. Because the general formula is H2N, this will mean that it's C3H6. And that's how you actually use the formula to help yourself know whether it's an alkane or an alkene. And that is the second method. The third method to know whether it's an alkane or alkene is to look at the structure. Structure meaning to say that they have already drawn out or you have already drawn out to look at how the shape looks like. For an alkane, you realize that the entire structure here is what we know as a saturated structure, or in this case, a saturated hydrocarbon. So what do I mean by saturated? Saturated means, if you look at the entire structure, there are only carbon to carbon, or I'll just use CC, single bond. That means all the bonds that you see between the carbons are all single bond, a single line over there. That's your single covalent bond. On the right hand side, when you look at your alkenes, you will realize that the alkene looks a bit different because of this structure that you see over here. And this is why we call our alkenes unsaturated hydrocarbons. And when we say unsaturated, what we mean is that it contains C double bond. Alright, so what you're looking at over here about these lines, these are not just normal lines or dash or equal sign. These are actually your covalent bonds. Right, so just a quick recap. For alkane and alkene, how do you tell them apart? First, look at their name, if it's given to you, or you can look at the formula and compare it to the general formula over here, or you can actually look at the structure itself to see whether you can see this very unique shape for alkene, which is our CC double bond. This is also what we call a functional group. Whereas for alkane, they are all single bonds over there. That's where you have your saturated and unsaturated hydrocarbon. So remember students, first start by recognizing whether it's alkane or alkene. Now once you have figured out whether it's alkane or alkene, let's move on to the second page over here, whereby in the notes, you actually taught about this thing called trends in physical properties. Trends in physical properties refers to what if we were to move down the family of alkane and alkene. For instance, if we were to go from methane to ethane to propane to butane, so on and so forth, what are we expecting to change in terms of the physical properties like melting point, boiling point, etc.? What if we go from ethene to propene to butene, so on and so forth? What are we expecting to change in terms of the physical properties? So the good news is that there's actually only one set of things to understand, because both alkane and alkene have the same pattern in terms of their trends in physical properties. So whether you're going down alkane or whether you're going down alkene, everything on this slide can be applied. Number one, melting point and boiling point increases for all alkanes and alkenes as you move down. Why is that the case? Because there is an increase in the size of the molecule. How do I know there's an increase in the size? You realize that there will be more carbon and more hydrogen as you go down. So in terms of the drawing, it will get bigger and bigger and bigger because there's more carbon and more hydrogen. When that happens, there's an increase in the strength of intermolecular forces of attraction. Then this will in turn cause more heat that's needed to overcome the attraction, and therefore the melting point and boiling point increase. The second physical property that we need to know is this property called viscosity. Viscosity refers to the stickiness of the chemical. Think of an oil that's flowing down. Think of honey that's flowing. Think of a glue that's flowing. These are what we call viscous liquids. So as you go down the homologous series, as the molecules get bigger, there is an increase in the viscosity. Last, both alkane and alkene, they are always insoluble in water, but soluble in what we call organic solvents, right? So they can never dissolve in water, but they can dissolve in what we call organic solvents. So there you have it. This is the second key thing for this chapter. Straightforward as it is, you need to remember the trends in terms of the physical properties of your alkane and alkene. Now let's move on to the last part of this video, where we are going to compare alkane and alkene in terms of their reactions. Right? We know that reactions means we are doing something to the chemical and something new will happen. This will also mean that maybe there's a need to write chemical equation. Maybe there's a need to write formula. Maybe there's a need to balance the equation. So let's start off with on the next page in terms of chemical reaction. Let's zoom in straight to the first part of the screen, which is the chemical reaction known as combustion. Right, so let me just cover up the rest of the portion so that it doesn't distract you. Now, combustion refers to the burning of the chemical in the presence of oxygen. And in our syllabus, we are interested in what we call complete combustion. Complete combustion would mean that you're actually burning it in what we call excess oxygen. That means there's a lot of oxygen there, and the product is always going to be CO2, which is carbon dioxide, and H2O, which is water. Now, what is shown over here is just some examples of the equation. If you have this chemical C3H8, which is an alkene, because if you recall, alkene has a general formula of CnH2n plus 2. Remember, the first thing in this video is how to recognize. Right, so if you can look at the formula, you should be able to derive that this is actually something that belongs to this formula, while this is something that belongs to this formula. Right, and in the reaction of complete combustion, always remember, you are burning the chemical. Burning something requires oxygen, so you must add with oxygen. And combustion, the idea is that you will always form CO2 and H2O. So then you write out your products. That's when then you balance it. Now, balancing is a skill. It takes a while, but you need to keep practicing so you can get a hang of it. Right, so this is a reaction that is common for alkane and alkene. Both can go through complete combustion if there's excess oxygen and heat. But what makes them special about the two is that there is a difference in terms of this kind of reaction, one known as substitution and the other one known as addition. Now, students from my class, you know that substitution is like playing a match of games or sports, like soccer, like basketball, etc. You are going for a one-to-one sub. You are changing one at a time. Now, addition is just like how the name says. You are just going to add it in. You don't really care what will happen. You're just going to add the thing in and see how the product will form. There's no need to take out anything. You're just adding it in. For substitution, always remember that you need to have UV light. For addition, always remember that the CC double bond is going to break. This is the reason why addition is only for our alkenes, whereas alkane can only go through substitution. So let's take a quick look at what substitution means, so that hopefully we can run through some of the examples and make you a bit clearer in terms of the process. So over here, I have two examples of an equation. One is this chemical here. It's a 2-carbon alkane, right? If you look at the whole structure, there's only single bond, and each of the carbon has their 4 bonds. The formula is C2H6, etc. You're going to add this with chlorine, which is Cl2, in the presence of UV light and in the presence of UV light. Now, what will happen in terms of substitution? Substitution means one of the chlorine here, just one of it, is going to replace one of the H over here. So it's going to be a 1-to-1 swap. Right? So what will happen now is, the product that's formed, you will still have most of the structure staying as per normal, but one of the H, and it can be any of the H here, will actually now be substituted by a chlorine, one at a time only. Each time, you can only substitute one at a time. And in the process, the H is out, and there's still one more Cl, right? That's where you have your H combining with the Cl as a chemical, which is HCl. Right? So this is actually how the substitution actually looks like. So once again, if you focus on my laser pointer, the chlorine actually replaces the hydrogen, and in the process, it forms this product, and the hydrogen combines with the other chlorine that's out there. So this green highlight chlorine came in to substitute. This yellow highlight hydrogen came out to form the new product. So that is how substitution could look like. Now, but if you look at the second example over here, what if the structure already has a chlorine here, but is still considered a type of substitution reaction? So now, you can only do 1-to-1 sub. This chlorine will now find another hydrogen, any of this, to do a substitution. So your product could look like this. Substitution will happen, and the hydrogen that comes out, just like the one above, will combine with the chlorine, and this time round, what happened was, this chlorine actually came in over here, and this hydrogen actually got substituted out if you follow the highlighter. Right, so this is actually what substitution means. It's a 1-to-1 exchange in the presence of UV light for alkane only. Please take note, it's only for alkanes. Alkene can only go through what I call addition. Then now your question might be, what does addition look like? Now, addition means to add on something new, right? And when we add on something new, the reason why alkene can do this is because they have this very special thing called a CC double bond. And what can happen here is that this CC double bond can actually break. When they break, it opens up and allows the carbon to form new bonds. So now, if it breaks, it will now look like this. Similarly, you still have your 4H, but this time round, you will see these two lines sticking out. These are the new bond that comes out. Where did it came from? It came from one of these lines of the double bond. What gets added on? It must be the chlorine. And this time round, you can add both of your chlorine in, and this is how an addition actually looks like. It doesn't require UV light. Sometimes you need to use heat. Sometimes you may need to put some catalyst, etc. But generally, this is what happens. Then for the one below, similarly, this CC double bond, one of the bond is going to break. And when it breaks, the carbon, everything is going to stay the same. Just that now there will be one new bond coming out. And this time round is to accept in the H's. In this case, you form this chemical over here. For those of you who are a bit more alert, you'll realize that this last equation that I show you over here is actually going from what we call ethene, C2H4, to what we call ethane, C2H6. Now this is actually a type of process that we use to convert vegetable oil into margarine. Right, this can be found in your notes in terms of the application of these few reactions over there. So there you have it. In summary, Alkane and alkenes, in terms of their reactions, both of them can go through complete combustion, but only for alkane, you can have this thing called substitution in the presence of UV light, whereby there's a 1-to-1 sub of each of the H. So you can keep repeating and repeating and repeating until you sub away all the H, but each time you can only sub one H. On the other hand, addition. Addition is about breaking the bond of the CC double bond, and then accepting new members in, and then that's how you form the other chemicals. Right? And one final bonus page. Now, in an alkane and alkene, this is all you need to know in terms of the comparison. But in the chapter itself, there's also this concept known as cracking. Now, cracking is a process that requires heat and a catalyst. Right? The catalyst can be any kind of chemical. It really depends on the type of reaction that we're looking at. But I think what is more interesting that I need to know is that what exactly does cracking mean? Cracking means that if you were to be given a piece of, let's say, a circle over here, how a cracking look like is you will just break it into small parts. And maybe this will be the remainder of the thing. It's literally cracking the substance. But of course, in chemistry, cracking can't be just drawing a circle that's been broken up, right? So what does cracking actually mean? Cracking means that sometimes we are given very, very large molecule like this C20H42. A very, very huge molecule because there's 20 carbon inside and 42 hydrogen. How would cracking look like is that you actually turn it into smaller ones. For example, CH4. For example, C2H6. For example, C5H10. For example, C6H12. So on and so forth. That is cracking. But always remember, all the carbon must add up to form the original carbon. All the hydrogen must add up to give the original hydrogen. So as a student, it's really just about counting, right? So long as you count, you should be able to find out what is the chemicals that can come out. So what exactly is cracking? Cracking is a process whereby larger molecules are being broken into smaller molecules. And then you might be wondering, why do we even do cracking, right? Why must I have the small molecules? And the reason is because smaller molecules are more useful to form other chemicals. Alright, and this is actually the more or less the last part of this chapter. Now in the notes, you realize a lot more application. So there will also be this thing called polyunsaturated fats. There will be this part known as the use of different vegetable oil or animal oil, trans fat, cis fat, etc. These are all content to help you understand the application of the concept of organic chemistry or hydrocarbon in this case. Yep, and that's all for this video.